Welcome to the RBFS Fundamentals Training Series. In this video, we will cover the Border Gateway Protocol. Due to the complexity of the protocol, we have split the material into two parts. In this first part, we will focus on the basics of the Border Gateway Protocol and show how to create a simple configuration in RBFS. We will also demonstrate some CLI commands for monitoring and debugging. The second part will deal with more advanced options. All configuration examples and demos in this clip are based on RBFS version 24.9.1. Before we dive into the basics of the Border Gateway Protocol and its implementation in RBFS, a brief disclaimer: this clip is free to use for non-commercial purposes and is designed to help you become familiar with RBFS through self-study. However, please note that it does not cover all configuration options available in RBFS, and implementation may change in future versions. Before we dive into the content itself, let me give you a quick roadmap of what we'll be covering. We'll kick things off with an introduction to the Border Gateway Protocol, where we'll break down its core mechanisms and message types. Then, we'll take a closer look at BGP path attributes and explore how they work. Next, we'll configure two BGP peers on a live system, step by step. Along the way, we'll also introduce some useful CLI commands for monitoring and troubleshooting the BGP setup. And to wrap things up, we'll dive into IPv6 support in BGP. Looking ahead, in our next video, we'll explore some key features of internal BGP, dive into route reflection, and introduce labeled BGP. We'll also cover methods to fine-tune BGP, bring in communities, and discuss some advanced BGP security mechanisms, including flow specifications. In the following section, we will give a brief introduction to the Border Gateway Protocol, short BGP, and present the basic mechanisms. If you are already familiar with BGP, you can skip this section. The Internet can be described as a global network of interconnected public IP networks, which are referred to as autonomous systems. Companies that provide access to the Internet are called Internet Service Providers, and the Border Gateway Protocol is used to route traffic between these systems. To understand BGP, it's important to first distinguish between an interior gateway protocol and BGP. An IGP is a routing protocol that exchanges routing information within an autonomous system to find the optimal path from source to destination. Examples of commonly used IGPs include OSPF and ISAS. An autonomous system, short AS, is a collection of networks under a single technical administration. While some definitions may describe it as a collection of routers or IP prefixes, the key idea remains the same: an AS consists of devices sharing the same routing protocol and routing policy. Each autonomous system is assigned an Autonomous System Number, AS number. The Internet Assigned Numbers Authority is responsible for allocating AS numbers, while regional Internet registries such as RN, RIPE-NCC, or APNIC manage as number distribution within specific regions. Initially, AS numbers were 16-bit unsigned integers, ranging from 1 to 65535. A portion of this range, 64512 to 65535, is reserved for private use and will not be routed on the Internet. Additionally, AS numbers from 64496 to 64511 are reserved for documentation purposes. As the Internet grew, the 2-byte AS number range became exhausted, leading to the introduction of 4-byte AS numbers. For these 4-byte AS numbers, the range 65536 to 65551 is reserved for documentation, and any AS number greater than or equal to 420.000.0000 is designated for private use. In this presentation, AS numbers from the private range are used to avoid using AS numbers allocated to organizations. The Border Gateway Protocol, BGP, is mainly used to exchange routing information between different autonomous systems. As a result, BGP is sometimes referred to as interdomain routing. This protocol is essential for the Internet's routing infrastructure, helping different networks communicate effectively with each other. BGP is the most feature-rich routing protocol in use today. It not only supports a single metric but also offers a variety of options that can be used to select, modify, and influence routing paths. A major advantage of BGP is its scalability, supporting millions of IP routes. Additionally, BGP provides flexibility in routing decision-making, making it ideal for large-scale networks. Another key requirement of BGP is security, as it allows the implementation of policies to ensure the integrity of routing decisions. Since routers from different autonomous systems may not always be trusted, security mechanisms are critical for preventing malicious or accidental disruptions to the network. The latest version of BGP, BGP v4, is defined in RFC 4271 and includes several security enhancements. BGP is commonly used in transit networks, which allow IP traffic to pass through one autonomous system to reach another. These networks are typically operated by Internet service providers and offer services to downstream customers. Transit networks interconnect either through private peering agreements or via Internet exchanges, which provide a neutral environment for multiple autonomous systems to meet. Additionally, BGP is required by multi-homed business customers or enterprises that connect to the Internet via multiple connections, either for redundancy or for increased bandwidth. Multi-homing can be implemented with either a single service provider or multiple service providers. A router capable of running BGP is called a BGP speaker. Two BGP speakers that form a connection and exchange routing information are called BGP peers or neighbors. BGP uses TCP as its transport protocol to provide a connection-oriented, reliable communication. Therefore, it does not need to implement retransmission or error recovery mechanisms. BGP runs on well-known TCP port 179. As the BGP session is considered reliable, there is no need to send periodic update messages, therefore only incremental changes are sent. However, BGP periodically sends keep-alive messages to ensure that the protocol layer is still operational. As a consequence of using TCP for session establishment between peers, BGP does not provide an automatic mechanism for detecting neighbors, which implies that you must explicitly configure a BGP peer address. When BGP is running between two peers in different autonomous systems, it is called external BGP, while running between two routers in the same autonomous system is called internal BGP. There are some significant differences between external and internal BGP. For example, as an eBGP neighbor is outside the local AS and there is no IGP running between two different autonomous systems, eBGP peers are usually directly connected, and the IP-TTL value of the BGP messages is set to 1. Within an autonomous system, there is an IGP running. Thus, iBGP peers do not have to be directly connected and IP-TTL value of BGP messages are set to 255. We have already learned that BGP uses TCP as a transport protocol. Each BGP packet consists of a 19-byte header, which contains a 16-byte marker field, a 2-byte length field, and a 1-byte type field representing the BGP message type encoded in this packet. The original specification defined 4 different BGP message types. The open message is the first message sent by a BGP speaker to initiate a BGP peering. The open message contains the BGP version number, which is set to 4, the AS number of the local router, and the hold time, which defines the maximum time between successive BGP messages. If the locally configured hold time and the one received in an open message differ, the lower value will be used. A value of 0 indicates that no keep-alive messages are sent. Additionally, the open message contains the BGP router ID, which is a 32-bit unsigned value usually represented as an IPv4 address. The router ID is most often automatically derived from the router's loopback address but can be configured manually. The open message may also contain additional parameters, such as specific feature capabilities. A BGP update message contains information about a path, which is represented by a set of path attributes. Path attributes are encoded in TLV format, meaning that each attribute consists of a triple, type, length, and value, where the length defines the size of the value field. Note that multiple different paths require multiple update messages, as a single update message can only carry one path. In BGP terminology, the list of destination prefixes is called Network Layer Reachability Information, NLRI. Multiple NLRIs sharing the same path can be sent within a single update message. An update message may also include a list of withdrawn prefixes, which are no longer valid. Due to scalability and stability requirements, BGP uses triggered updates, which are only sent if there is a change in the network. Triggered updates help reduce the load on a BGP speaker. A BGP notification message is sent whenever an error occurs to inform the BGP neighbor. After a BGP notification is sent, the BGP session is immediately closed. The notification message contains the error code, the error subcode, which provides more specific information about the error and depends on the error code, and a variable length data field to provide more information for diagnosis. As an example, a notification message may have an error code of 2, indicating an open message error, and the error subcode of 5, which means authentication failure. A TCP-based BGP session does not provide any means of verifying the presence of a BGP neighbor. After BGP establishes the TCP session, the only method of verifying neighbor presence is to actually send BGP traffic. However, there are often long periods of time when no BGP updates are sent between neighbors. BGP keep-alive messages are exchanged between BGP peers periodically to ensure the BGP session is still functional. Keep-alive messages are sent at a period of 1/3 of the hold time. If the hold time is set to 0, no keep-alive messages are sent. Route refresh is an additional BGP message introduced in RFC 2918. Whether two BGP speakers will use route refresh messages or not is negotiated by the peers during the exchange of open messages as part of the capability negotiation. Routers use the route refresh feature to request a neighbor to resend all the routing information when needed, without resetting the BGP session itself. BGP maintains a finite state machine for each configured peer to represent the various BGP peering states and define the transitions between them. This overview of the state machine will help you with troubleshooting. Initially, a BGP speaker is in the idle state. In this state, all incoming BGP connections are refused, and no resources are allocated to the peer. If the peer's IP address cannot be found in the local routing table, the state remains idle, and no attempt is made to establish a connection. Triggered by events such as configuration changes or the peer's address becoming reachable, the BGP peer state enters the connect state, initiates a connect retry timer, and starts the three-way TCP handshake by sending a TCP SYN message to the remote router. If the TCP handshake is completed within the connect retry time, an open message is sent to the peer, and the finite state machine advances to the open sent state. If the TCP handshake is not successfully completed, the peer state moves to the active state. In the active state, BGP tries to reinitiate a TCP connection. A common reason for this failure is that either the remote peer has no IP route to the source IP address or the remote peer is misconfigured, for example, with an incorrect IP address or wrong AS number. In the open sent state, three different things can happen. If the BGP speaker does not receive an open message from its peer, it will change to the active state. If the BGP speaker receives an open message, it will either send a keep-alive message and move to the open confirm state, or it will send a notification message and return to the idle state, depending on the validity of the received open message content. Two BGP speakers should only have a single BGP peering session between them. The router ID values that are part of the open message are used to detect if duplicate sessions exist. Only the session initiated by the router with the numerically higher router ID will be retained, while the other session will be dropped. In the open confirm state, BGP waits for a keep-alive message from its peer. If a keep alive message is received within the hold time, it moves from the open confirmed state to the established state, which is the only desirable state for a BGP neighbor, as it means that both routers have agreed to exchange updates. If no keep alive is received, the peer will send a notification message and return to the idle state. Now that we are familiar with the basic mechanisms of BGP and the individual message types, we want to dive a little deeper into the path attributes and explain how they contribute to the route selection process. We have already mentioned that in BGP, a route consists of a list of destinations carried in the network layer reachability information field, for example, IPv4 prefixes, along with a path, which is represented by multiple path attributes. Each path attribute is encoded as a TLV triple consisting of a 2-byte type field, a 1-byte or 2-byte length field, and a variable length value field that contains the attribute data. The type field itself is split into an attribute flags field and the attribute type code, which represents the attribute. The attribute flags define whether the length field is 1 byte or 2 bytes, called extended length. The attribute flags are also used to classify a path attribute as well-known or optional, mandatory or discretionary, and transitive or non-transitive. Taking a step back, we know that BGP is an extremely feature-rich protocol, which means that it has evolved over many years with numerous enhancements. This has led to the situation where an older BGP implementation might not be aware of a recently added path attribute. Therefore, the path attribute flags encode how to handle a specific path attribute. If a path attribute is well known, it must be recognized by all BGP implementations. Otherwise, it is considered optional. A well-known path attribute might be mandatory, which means that it must be included in every update message. Otherwise, it is considered well-known discretionary. Path attributes that are not well-known are called optional. It is not required for a BGP implementation to support all optional attributes. The way a BGP implementation deals with an optional path attribute that it does not support is described by the transitive flag. A transitive path attribute is accepted and passed to other BGP peers. If a transitive path attribute is not implemented, the partial flag is set to indicate that the attribute was not understood by the local router but still passed along. A non-transitive path attribute is simply ignored if it is not supported by the local router. The AS path is a well-known mandatory attribute and represents the autonomous systems that need to be traversed to reach the destination. Historically, there were two different components of the AS path attribute, the AS sequence and the AS set. The AS set was deprecated, so today only the AS sequence is used. The AS sequence is a variable length list of AS numbers, where the rightmost or first entry represents the originator autonomous system. Whenever a BGP peer advertises a route to an external peer, it adds its local AS number to the AS path attribute, but it does not modify the AS path when advertising a route to an internal peer. Thus, the AS path attribute is empty when a local route is inserted into the BGP table. The AS path attribute is very important because it is the primary attribute used to avoid routing loops in BGP. When a BGP speaker receives an update message, it examines the AS path attribute and checks that its own AS number does not appear in it. If the AS number does appear, the route is discarded to prevent a loop. The BGP next hop is a well-known mandatory attribute that identifies the IP address a router should use to forward packets toward the destination announced in a BGP routing update. In the case of eBGP, the sending router sets the next hop attribute to its own IP address, while in case of iBGP, the next hop is not changed by default. If the next hop attribute shares the same subnet as the eBGP peer to which the update message is sent, then the next hop is not updated to avoid suboptimal routing. This situation is common, especially on Internet exchange points. In general, the next hop IP address can be set to any valid IP address. This feature is quite useful for traffic steering, as well as denial of service mitigation, such as in remote-triggered blackholing. It is assumed that the next hop has the same address family as the prefix being advertised. For instance, an IPv4 prefix has an IPv4 next hop, and an IPv6 prefix has an IPv6 next hop. We will see in Part 2 that this assumption is not always true, especially when dealing with VPN routes. The BGP origin is a well-known mandatory attribute that describes the source of the prefix. The origin attribute can take one of three possible values. IGP describes a prefix originated by an IGP, Interior Gateway Protocol, running inside the local autonomous system. EGP represents a prefix taken from the Exterior Gateway Protocol. This was used during the migration from EGP to BGP but is no longer seen today. Incomplete, typically represented by a question mark, is a prefix learned from an unknown source, such as through redistribution of static routes into BGP. Once set, the origin code should never be modified. So far, we have covered three well-known mandatory BGP path attributes, which are the only ones of this attribute type. To ensure completeness, we provide a list of the most important path attributes used today, along with their attribute type and a reference to the document where they are defined. We will cover most of these attributes in more detail in the next video. All of these attributes can influence the path selection process, which we will address in the next slide, either directly or indirectly. Typically, a BGP router receives multiple paths for the same destination. As we've already seen, BGP supports several path attributes that help determine which path to install in the routing table and use for forwarding. Before the actual path selection process begins, all paths with an invalid next hop are eliminated. Then, the BGP path selection process narrows down to a single best path, eliminating any other paths, unless there is a route preference from another routing protocol that takes precedence. The first criterion for selecting the best route is the lowest route source. A route from the local route source is always preferred over a received route. For example, if the same prefix is redistributed and received from a neighbor, the local, redistributed, route will be preferred. If multiple paths still exist, the path with the highest local preference value is preferred. Note that local preference is the only BGP path attribute where the higher numerical value wins. Next, BGP considers the shortest AS path, which reflects the number of autonomous systems the route has traversed, regardless of the size of the particular AS. If multiple paths remain, the path with the lowest origin type is chosen. The hierarchy of origin types is as follows: IGP has the lowest value, followed by EGP, and incomplete has the highest value. If all origin codes are the same, the path with the lowest multi-exit discriminator is preferred. By default, MED values are only compared and the routes are learned from the same autonomous system. At this point, it's clear that the destination network lies outside the local AS and that the alternatives are fairly similar. Since the IP packets must exit the autonomous system, it is preferred that they do so as quickly as possible. If any of the alternatives are received from a BGP peer in another AS, that route will be preferred. The distance to the exit point is calculated by comparing the IGP costs of the BGP next hops, as indicated in the routing table. There are additional tiebreakers that can be considered, which we will not delve into here. Finally, it's important to remember that BGP was not designed to find the optimal path in terms of bandwidth or shortest distance from the source. Instead, BGP focuses on policies that allow traffic manipulation, typically driven by business logic. From this algorithm, it's clear that the most significant attributes influencing best path selection are the local preference, AS path, and MED. Up to this point, we covered a lot of theory. Now, it's time to put this into practice and configure a BGP peering in RBFS. For this demonstration, we are using a consolidated BNG image running RBFS version 24.9.1.1 in a virtual environment. The instance named default will be used for our BGP configuration. Currently, no routing protocols are configured. For simplicity, a couple of interfaces, including a loopback interface, have already been pre-configured and assigned to the default instance. The BGP configuration is done using the set instance name protocol BGP CLI hierarchy. As previously mentioned, we are using the instance name default. First, we need to define a few global parameters that apply to all BGP peers. The most important of these is the local AS number. We also define a BGP hostname, which is useful for troubleshooting since it allows us to identify which peer router corresponds to which IP address, eliminating the need to remember IPs. The BGP hostname is part of the optional capability negotiation during session establishment. Setting the router ID is not strictly necessary as long as it matches the address already defined under the set instance default hierarchy. If no router ID is configured, the IP address of the loopback interface will be used. Additionally, we need to activate all address families that should be supported by BGP. For this demonstration, we will stick to IPv4 unicast only. Next, we need to define a BGP peer group. In RBFS, configuring a BGP peer without a peer group is not possible. The peer group configuration requires a peer group name, which can be chosen based on your naming conventions. Since keywords in RBFS are lowercase, I prefer to use uppercase letters for profile names. In this case, we will use the name ISP2. The peer group configuration, in its simplest form, requires setting the remote AS number and activating the supported address families. Again, we start with IPv4 unicast only. Finally, we need to define one or more BGP peers using the set instance default protocol BGP peer command. We must specify that we are using an IPv4 address to define the peer. Afterward, we set the peer's IP address, followed by the source IP address of the local router. Lastly, we associate the previously defined peer group with this peer and commit the entire configuration. The show BGP peer command can be used to get a list of all configured peers and its state. We can see that we have 2 BGP peers configured. Unfortunately, both peers have not reached the state established. Let's start troubleshooting with peer 172.16.0.6, which is in state active. This indicates that there the peer IPv4 address is reachable, but for some reasons, the session cannot be established. Let's take a closer look at this peer using the detail keyword. It seems that both peers have already exchanged BGP open messages, but the local peer has closed the connection with a notification of type open message error and a subcode of bad peer AS. Now, that's interesting. Obviously there is a AS number mismatch either on the local side or the remote peer. We can use the capture interface command to monitor packets exchanged. The peer is directly connected to interface hostif 0/0/2 and we are only interested in incoming packets. We can also restrict the packet capture to BGP packets to reduce the output. Looking at the first open message received, we see that the remote peer has set its AS number to 64503. Remember that we have configured the peer group ISP2 to use remote as 64502. We can easily fix this by creating a new peer group named ISP3 with remote as 64503 and assign it to the peer. After committing the new configuration, the BGP session is established. The remote peer indicates itself as R3. We now turn our attention to peer 172.16.0.2. Using the show BGP peer command with the peer address as an option reveals that there was no exchange of BGP messages so far. So, we need to find out why even the TCP connection setup fails. Using the ping command, ensure that we have IP connectivity. Once again, let's monitor the directly connected interface, in this case hostif 0/0/1, for incoming packets. The very first packet received is a TCP SYN packet. It seems that the remote side wants to use TCP authentication option with key ID 1. Up to now, we have not configured any peer authentication. From the output, we cannot extract the passkey, so we need to agree this offline with the administrator of the remote peer. TCP authentication option, introduced in RFC 5925, is an additional field in the TCP header that allows for robust authentication mechanisms and enabling key changes without disrupting existing sessions. This option supports multiple message authentication codes and provides better protection against replay attacks, making it more secure than its predecessor, the TCP MD5 authentication. An authentication option can be used by multiple peers. The TCP authentication option is configured using the set instance default TCP authentication CLI command hierarchy. We define a profile named sample_auth and set the type to HMAC SHA-256, the key ID to 1 and the secret key to Rtbrick. Afterwards we associate this authentication profile with the peer definition and commit the configuration. Let's take a short break to summarize the configuration we've created so far. For a minimal BGP configuration, we must define some basic parameters using the set instance name protocol BGP command, especially the local AS and the supported address families. Secondly, we create a peer group in which the remote AS number and the supported address families are defined. This address family configuration is not redundant as the BGP instance might support multiple address families, but we may want to exchange routes for only a subset of it with a particular peer. Thirdly, the peer itself is configured including the peer IP address, the source IP address for this peering, and the peer group this peer belongs to. Optionally, TCP authentication option can be added and assigned to the peer configuration. This slide can be used as a kind of reference. If you need more time to review it, please pause the video. When we introduced the BGP Keep Alive message, we learned that they are sent periodically. The interval between two successive Keep Alive messages is defined by the Keep Alive timer. A notification message sent and the session is closed, if there are no Keep Alives received within the hold time, which is 3 times the Keep Alive time. We can modify the Keep Alive time and the hold time using the set instance default protocol BGP timer command. Let's set them to new values and commit the configuration. Looking at the details of peer R2, we can see that these values are now different on both ends of the BGP session. In case of a mismatch, both peers agree on the lower value. For a review, I've put the commands shown into this slide. At this point, we like to highlight that it is best practice to keep the timers at conservative values as the Keep Alive timer is not the preferred way to speed up network convergence in case of failure. There are more advanced options available such as using bidirectional forwarding detection protocol between the peers. So far, we have configured 2 BGP peers and from the show BGP peer command we can see that we have received 7 prefixes from each peer and that we have advertised 7 prefixes to each peer, thus our local BGP instance sends route update learn from one peer to the other, but it does not advertise any routes from its own AS to its peers. In contrast to IGP protocols, BGP does not have interfaces associated to it on which it natively runs. Thus, all networks and routes that you want to advertise to other peers need to be imported into BGP using a process that is called redistribution. Sources for redistribution can be either directly connected interfaces, static routes, or other routing protocols. In order to demonstrate redistribution, let's first configure a static route with a next hop profile set to the null interface. Next, we import this route using the set instance default protocol BGP address family IPv4 unicast redistribute static command. This command redistributes all static routes present on the local system into BGP. In a real-world scenario, you should add a policy to control which routes are redistributed. We will come back to policy configuration in the next video. After activating the configuration, we can see that the local peer now advertises 8 routes to each of its peers. We conclude this section on basic BGP peer configuration with this slide which sums up the redistribution configuration. We managed successfully to establish 2 BGP peerings. Before we move on, we want to demonstrate some more commands to help monitoring and troubleshooting. The general settings of BGP can be extracted from the Show BGP Summary command, which provides the hostname, the local AS number, the BGP version, as well as the protocol preferences. The protocol preference controls which routing protocol the routing protocol daemon prefers in case the same prefix is learned from multiple sources. In addition, some configurable options in the path selection process are displayed. We've already had a brief look at the Show BGP Peer Detail command. You can use either the peer IP address or the hostname to restrict the output to a single peer. The output reveals the peer IP address, router ID, and AS number of both the local and remote peers, along with the authentication method in use. More interestingly, the list of NLRIs is shown. The output indicates that the local peer supports IPv4 unicast, and the remote peer supports IPv4 unicast as well, meaning both peers have agreed to use this address family. If the list of sent and received address families differs, the peers agree on the common subset. If we move to the next page, we will also see various packet statistics. The Show BGP TCP connection command provides information about the underlying TCP connection, including authentication. When BGP peers exchange route updates, it can sometimes be useful to inspect the flow of information. The Show BGP RIB in command highlights all routes that have been received from the BGP peers. Since the output can become quite long, the command offers options to restrict the output by adding filter options for the address family, peer, or a specific prefix. We can add the option default to get some more information, for instance attached community attributes. All routes from the RIB in are used as input for the route selection process. As a result, BGP populates the BGP fib, which can be inspected using the Show BGP fib command, for example, the prefix 192.168.0.104/32. Returning to the RIB in, we see that we have learned this prefix from both peers, R2 and R3. We already know that the BGP route selection process provides a single best path. As the local preference, AS path length, and MED are identical, the lower router ID was used as a tiebreaker. We can configure BGP to install multiple active paths into the fib if the routes are equivalent up to the MED criteria. This can be done via the set instance default protocol BGP address family IPv4 unicast multipath command, which takes the maximum number of active paths as an argument. After committing the configuration, we can see that we now have 2 active paths to all destinations in AS64504 installed in the fib. While the Show BGP RIB in command lists all routes that were received from BGP neighbors, the Show BGP RIB out command shows all routes that are advertised to BGP peers. Remember that updates are generated on a per peer group level. From the output, we can see that the local AS number is prepended to the AS path before the route is advertised, as both peer groups represent external BGP neighbors. Note that the local preference is not set because both peer groups represent eBGP peers, and local preference is only used with internal peers. Also, the MED value is set to 0 for all routes. We will show how to modify the MED or local preference values for each individual route using policies in the next video. It's also possible to set the MED and local preference for all updates globally using the Set Instance Default Protocol BGP MED and Set Instance Default Protocol BGP Local Preference commands. Again, I have put together the commands that I just showed you into a couple of slides as a reference. The most important takeaway is that we have the Show BGP command hierarchy for all BGP-related monitoring commands. The Show BGP peer command provides all information about the BGP neighbors, while the Show BGP rib in, Show BGP rib out and Show BGP fib commands are used to get information about routes in various stages. All of these commands provide additional CLI options to further restrict or filter the output. You can use the question mark at any point to get a feedback on the supported CLI options. Now that we are familiar with basic BGP configuration for IPv4, we will look at how IPv6 is implemented in BGP. The material presented in this section is applicable for IPv4/IPv6 dual stack sessions as well as for IPv6 only scenarios. The original BGP specification defined the next hop field as well as the NLRI field carried in the update message to be IPv4 specific. To support IPv6 in BGP, both of these attributes cannot be used and must be replaced with new attributes that provide sufficient flexibility. RFC 4760 defines multi-protocol extensions that can be used to exchange routing information for non-IPv4 unicast prefixes. Two new path attributes are defined, the multi-protocol reachable network layer reachability information and the multi-protocol unreachable network layer reachability information. The MPReachNLRI path attribute contains an AFI, which stands for Address Family Identifier, that specifies the network layer protocol being used, such as IPv4 or IPv6. It also contains a subsequent Address Family Identifier, SAFI, which distinguishes between different types of routes, such as unicast, multicast, or VPN routes. The combination of AFI and SAFI defines the semantics of the next hop field and the NLRI included in this path attribute. In the case of IPv6 unicast, the AFI field is set to 2, for IPv6, and the SAFI field is set to 1, for unicast. This combination ties the next hop attribute to one or two IPv6 addresses, a globally unique IPv6 address and, optionally, a link local address. Whether two BGP peers will exchange multi-protocol extensions, and for which AFI-SAFI combinations, must be agreed upon during capability negotiation in the exchange of open messages. The MPUNRACHNLRI path attribute is used to withdraw routes that have become unavailable. At this point, I'd like to note that BGP uses TCP as a transport protocol, and TCP can run over both IPv4 and IPv6. The exchange of routing information is completely independent of the transport protocol in use. In addition, both IPv4 and IPv6 routing updates can be exchanged over the same BGP session. It is important to note that the BGP identifier remains a 32-bit unsigned integer, even if the BGP control plane session runs on top of IPv6. If we already have an existing IPv4-based BGP session and want to add IPv6 support, we can simply add the IPv6 address family in the RBFS configuration. This has to be done on three different levels: the instance level, the BGP protocol level and the peer group level. After activating the configuration, we can verify that the BGP peering to router R3 now shows that both peers support IPv4 unicast and IPv6 unicast, and that they have agreed to use both address families. For clarity, the commands that I have just configured on the system are listed here. Some configuration options that we have learned while configuring IPv4 are also available for IPv6, for example the multipath option or the redistribution of static or IGP routes into BGP. Both are applied at the set instance default protocol BGP address family IPv6 unicast level. I have also highlighted the relevant part of the show BGP peer command output. Once again, both peers can be configured with a set of different address family and subsequent address family identifiers and the agree on a common subset. The CLI commands shown in the previous section are identical for IPv4 and IPv6. Let's have a look if we have received any IPv6 routes from our neighbor using the show BGP ribbon command restricted to IPv6 unicast. As you see, we have received 2 IPv6 routes. You might have already noticed that the next hop is an IPv4 address, although I told you that NLRI and next hop should have the same address family. If the BGP session is configured to use IPv4 as the peering address, external BGP automatically uses the peer address as the next hop in its updates. However, when using an OFI-SOFI of IPv6 unicast, the next hop must be an IPv6 address. How does this work together? IPv6 provides a mechanism called the IPv4 embedded IPv6 address, which allows IPv4 addresses to be encoded within an IPv6 address. In the introduction to this section, I told you that it doesn't matter whether the BGP session runs over IPv4 or IPv6. Therefore, we'll conclude this section by configuring an eBGP session to an IPv6 peer. To do this, we first create a new peer group ISP5 for a neighbor in AS64505 that supports dual stack. In the peer configuration, we now need to specify IPv6 as the address type. Apart from this, the syntax remains the same, first the peer address, then the local source address, and finally the reference to the peer group. After activating the configuration, we see that we now have a third BGP session with router R5. The show BGP peer R5 command output tells us that, no surprise, the peer addresses are IPv6, and the list of NLRIs shows that both peers support IPv4 and IPv6 unicast. Let's also take a quick look at the ribbon. We see that we learned 3 IPv6 prefixes from R5 with an IPv6 next hop. This time it's a native IPv6 address, instead of an IPv6 embedded IPv4 address. However, we didn't learn an IPv4 prefix. If we also want to support IPv4 routes over an IPv6-based BGP session, we again face a problem with the mismatch of the next hop address family. We cannot use the standard next hop path attribute as it only supports IPv4 next hops, and we now have a IPv6 peering address. To resolve this issue, we need to encode IPv4 routes in a mpeer-each NLRI instead of a standard NLRI, which allows us to define a new semantic for the next hop. RFC 5540 defines a method called extended next hop, which allows IPv4 NLRIs to be advertised with an IPv6 next hop address. Both peers need to agree on using this feature as part of the capability negotiation during BGP session establishment. Enabling extended next hop is done via the set instance default protocol BGP peer group command for the IPv4 unicast address family. After committing the configuration, we can verify that we now learned IPv4 prefixes with IPv6 next hops on this session. The show BGP peer command also reveals that the extended next hop is negotiated for IPv4 unicast. I hope you enjoyed this clip on configuring BGP basics in RBFS. Thanks for your attention and see you soon for the second part.